Hello, everyone. And today we're going to continue with our discussion about stoichiometry. And really, we're going to we're going to get in depth of really what stoichiometry is today. And we say that we can use stoichiometry to help us predict needed amounts of reactants or made amounts of products. Let me write that down for you. Stoichiometry to predict amounts of reactants or products from equations. Linear equations or we'll say formulas for now. So let's look at an equation. Al2O3, commonly known as aluminum oxide, can become aluminum plus oxygen. And look, there's our friend. There's a Hofbrinkel, right? So that's what I meant by Hofbrinkel, that over here, the oxygen doesn't have to be in a diatomic. Over here, when the oxygen is by itself, it does have to be a diatomic. Now, whenever we're doing stoichiometry, the first thing you always want to do, every single time, ensure the equation is balanced. And I purposely set this up. This equation is not balanced. To balance this, 2, 4, 3. In case you're wondering, I did have that answer written out. It would have taken me a couple more seconds to actually think about it, so I don't expect you to be that fast. But the idea behind stoichiometry is to be able to determine how much of one substance changes if we change another. So if we change this amount, how much would that amount change? Or if we need a set amount of the products, how many reactants would we need, right? Because this recipe only tells us a set ratio. It tells us that if we have 2 moles of this, this is how much we could make. Now, that doesn't mean that we only ever have 2 moles of aluminum oxide. I can have 1 billion moles. I can also have half a mole of aluminum oxide. But using stoichiometry, regardless of the amount of this, we can always figure out how much aluminum and how much oxygen. Okay, so let's look at an example question, see how it works. How many moles of O2 will be created from 12.72 moles of Al2O3, aluminum oxide, right? Because we can see up here in the equation that when we decompose aluminum oxide up here, it turns into aluminum and oxygen, right? So to do that, we have to remind that our recipe is always telling us the proportions, not necessarily the exact amount. But from the equation, we can tell that for every 2Al2O3, we create 3 oxygen molecules. And that is what we call a molar ratio. And we're going to actually use that in basically dimensional analysis. Let me show you how this works. So we know we have 12.72 moles of Al2O3. And we want to convert that into O2. So we're going to write out our proportionality of 3 moles of O2 over 2 moles of Al2O3. That equals, if you take your calculators out, 0.08 moles O2. So what we did here is we used this right here, and that's what we call a molar ratio. And molar ratios are always from a balanced chemical equation. So we looked up here at our balanced chemical equation, right? We saw what our molar ratio is. That's where this number is coming from, always from the balanced chemical equation. Reminder that this isn't necessarily the amount of stuff we have, nor the amount of stuff we're making. That's just the ratio to convert. Just like we were talking about in class, where you can have a recipe where I can, if I needed pancakes, I can specifically say, if I want to make 6 pancakes, how many eggs would I need? Do I need more than eggs? Of course, but I don't have to talk about that here. Let's look at a second example. Okay, so our next one, I'm going to be nice and I'm going to balance this for you, is, and let me zoom in a little bit. We're going to take some gold. Let's take some gold and some hydrogen gas. Actually, I'm sorry, that's hydrogen sulfide. That's a salt. And we're going to create hydrogen gas and some gold sulfide. Not the cheapest way to make hydrogen gas, right? Question. How many moles of H2 are produced from, let's say 22.1 moles of AU. So same thing. I'm going to look at my equation and I'm going to note that H2 and AU, that's what we're comparing. So I see my AU and I see my H2, and I'm going to set up that molar ratio based on my balanced chemical equation. So in the problem, I have 22.1 moles, and I can highlight this. So I know I'm using this and this as my molar equation. Here's what I'm starting with. So I have 22.1 moles of AU times 3H2 over 2AU. And if you take out your calculators, you will find that that equals 33.15 moles of H2. No, you don't have to put the of. You can just write moles H2. Now, I know some of you are probably thinking, but Mr. Schreiber, you can't make H2 from AU just by itself. Yes, that's not what we're saying. Remember that stoichiometry is always based on a chemical equation. So it's not saying that if we just had moles of H2, just had moles of AU, how much H2 could we make? What we're saying is that given this recipe, because it all comes back to the recipe, given this recipe, assuming we had 2 AU, theoretically, how much H2 could we make? In fact, you can once go ahead and say that if not stated, as long as it's not stated, you may always assume you have enough of the other substance. What do I mean by that? I'll show you in a minute. So even though it's not stated, we can assume that even though we're talking about just AU and H2, we can assume that we have our H2S. And how much do we have? More than enough. We just have enough. We don't even care. That's the power of stoichiometry, in that we can completely skip how much we need there. We can just say, if we had this much gold, how much hydrogen would we be making, right? And that's how stoichiometry works. Okay. We will get more practice in class. Can't wait to see everyone. Have a good day, and bye.